Hello there, and welcome to Sleepy Science Vault. Beneath your feet, right now, the ground is moving. Not in a way you can feel. Not in a way that shakes the walls or rattles the windows. But slowly, quietly, over years and decades and centuries, the surface of our planet is in constant, restless motion. The Earth we think of as solid and permanent is, in truth, anything but. The outermost layer of our planet, the crust, is broken. Not broken in the way something damaged is broken, but divided, like the shell of an egg that has been cracked into dozens of irregular pieces. These pieces fit together across the face of the Earth, edges pressed against edges, some sliding past one another, some pushing underneath, some slowly pulling apart. We call them tectonic plates, and they have been moving for hundreds of millions of years. Most of that movement is almost impossibly slow. A few centimeters per year, on average, about the same rate your fingernails grow. And yet, over geological time, that slow crawl has reshaped entire continents, raised mountain ranges from flat plains, and opened vast ocean basins where dry land once stood. Even today, that movement is quietly reshaping the world we live in. The city of San Francisco, for example, is gradually drifting southward toward Los Angeles. The two cities are separated by hundreds of miles right now, but given enough time, tens of millions of years, that distance will shrink. The same geological forces that created California are still at work, still nudging the landscape in ways no single human lifetime could ever witness in full. At the heart of this movement in California is one of the most studied geological features on Earth, the San Andreas Fault. It stretches for nearly 900 miles, running through much of the western part of the state, and it is responsible for roughly 2/3 of all the horizontal movement California experiences. Year after year, the land on one side inches past the land on the other, accumulating distance, accumulating history. But not all earthquakes come from places like the San Andreas. Not all of them happen at the boundaries between major plates. Some occur deep within the interior of a plate, in regions that might seem, on the surface, geologically quiet. The Earth's crust is far more complex than any simple map can suggest, laced with ancient fractures and hidden weaknesses that can, under the right conditions, suddenly give way. These fractures are called faults, and they come in several different types depending on how the rock on either side moves relative to the other. In some faults, the two sides slide horizontally past each other. In others, one side is pushed upward while the other drops down. Some faults are nearly vertical, others tilt at low angles through the rock. Each type produces its own distinct pattern of shaking, its own signature in the ground. What is remarkable about some of these faults is that they do not always behave violently. Some of them move in a slow, continuous way called creep, a gradual, almost gentle slipping that releases stress without ever building toward a major rupture. Roads crossing these faults may slowly develop offsets over decades. Sidewalks may crack and shift. The movement is real, but it happens quietly, without drama. Other faults are not so patient. In those places, the two sides of a fault are locked together by friction, unable to move even as the tectonic forces pressing on them continue to build. The rock bends slightly, strains slightly, storing energy the way a compressed spring stores energy, invisibly, silently, for years or decades or centuries. Geologists call this elastic strain, and the longer it accumulates, the greater the energy waiting to be released. And then, at some point, the friction is no longer enough. The locked fault finally slips. In a matter of seconds, all of that stored elastic energy radiates outward through the rock as seismic waves, waves of compressed and sheared stone moving in all directions at once, faster than sound, powerful enough to travel through the entire planet and be detected on the other side of the world. That release, that sudden, violent unwinding of centuries of accumulated stress, is what we feel on the surface as an earthquake. It is, in a sense, the Earth simply finding its balance again. Releasing what was held too long. Settling, however violently, into a new position. And then, slowly, quietly, the process begins again. When a fault finally slips, something extraordinary happens in the rock. In the fraction of a second that the rupture begins, a point somewhere beneath the surface, sometimes just a few miles down, sometimes buried 50 or 100 miles into the earth, becomes the origin of everything that follows. That point is called the focus, or sometimes the hypocenter, and it is the true source of the earthquake. Directly above it, on the surface, is what we call the epicenter. The point on the ground closest to where the rupture started, the location that news reports will cite, the coordinates that will appear on maps in the hours after the shaking stops. But here is something that often surprises people. An earthquake is not simply a single point breaking. In a major earthquake, the rupture does not stay in one place. It propagates, it travels along the fault, tearing through rock in both directions from the initial break, sometimes for extraordinary distances. The 1906 San Francisco earthquake ruptured along nearly 300 miles of the San Andreas Fault. The Great Sumatran earthquake of 2004 tore through over 800 miles of fault in a matter of minutes. The rupture itself was moving, racing through the crust at speeds approaching that of sound and rock. All of that motion, all of that sudden tearing and sliding, sends energy radiating outward in every direction. That energy travels as seismic waves, and understanding those waves is really the key to understanding what an earthquake does to the world around it. Think of seismic waves the way you might think of ripples spreading across the surface of a pond after a stone is dropped in. The water itself does not travel outward. What travels is the disturbance, the energy, passing from one water molecule to the next in an expanding ring. Seismic waves work on a similar principle, except they move through solid rock, and they do so in several distinct and very different ways. The first type to arrive at any given location are called P waves, or primary waves. These are compressional waves, meaning they travel by alternately squeezing and stretching the rock in the same direction the wave is moving, much like sound waves travel through air. P waves are extraordinarily fast. In solid crustal rock, they can move at several miles per second. They are the first signal that seismographs pick up, and they can pass through almost anything: solid rock, liquid rock, even the fluid outer core of the earth. If you are near an earthquake, P waves might reach you before anything else, sometimes producing a sharp jolt or a brief, percussive sensation, almost like something has punched the ground beneath you from below. Following closely behind come the S waves, or secondary waves. These move more slowly than P waves, roughly 60% of their speed, and they behave quite differently. Rather than compressing the rock, S waves move it from side to side, perpendicular to the direction the wave is traveling, the way a rope shakes when you flick one end of it. This shearing motion is what makes S waves so damaging to buildings. Structures can generally handle vertical forces reasonably well. They are, after all, designed to resist gravity. But rapid lateral movement is far more destabilizing, and S waves deliver exactly that. By the time both P waves and S waves have passed through an area, the worst of the shaking is often felt. But there is a third category of waves that travel not through the body of the Earth, but along its surface, and these can sometimes be the most destructive of all. Surface waves move more slowly than either P or S waves, but they carry an enormous amount of energy, and they affect the ground in complex, rolling ways. Some surface waves cause the ground to ripple in a slow, undulating motion, almost like the surface of water during a gentle swell. Others cause the ground to twist and move in a figure-8 pattern that is deeply disorienting and devastating to anything built on top of it. Because they travel along the surface rather than dispersing through the volume of the Earth, they lose their energy more slowly, which is why major earthquakes can cause significant shaking at surprisingly large distances from the epicenter. The character of that shaking, what it actually feels like, how long it lasts, how much damage it does, is shaped by something called frequency. Seismic waves, like sound waves or light waves, come in different frequencies, meaning some oscillate quickly while others move in long, slow undulations. High-frequency shaking tends to be sharp and short-lived. Low-frequency shaking is slower and more rolling, but it can persist for longer and affect much larger areas. Tall, flexible buildings, skyscrapers and long-span bridges tend to resonate with low-frequency waves, amplifying the shaking in ways that shorter, stiffer structures would not experience. A short brick building, meanwhile, might be shaken violently by high-frequency waves while a nearby high-rise barely sways. The same earthquake can do very different things to different structures standing just blocks apart. One of the most important factors influencing all of this is how deep the focus is. A shallow earthquake, one where the rupture begins only a few miles beneath the surface, concentrates its energy in a relatively small area. The shaking above it can be intense, but it does not spread far. A deeper earthquake, with its focus 50 or 100 miles down, releases energy that must travel farther before it reaches the surface. By the time it does, it has spread out over a wider area, so the shaking is often less violent in any one location, but it can be felt across a much larger region. Deep earthquakes also tend to produce less surface rupture, the visible cracking and displacement of the ground that shallow quakes sometimes leave behind. There is something else about earthquakes that people rarely expect until they experience one firsthand, and that is the sound. Earthquakes are not silent. When seismic waves reach the surface, some of their energy translates directly into audible sound, particularly from P waves, which are compressional and behave similarly to sound waves to begin with. People who have been close to a moderate or large earthquake often describe hearing something before they feel it, a deep, low rumble, like a distant truck or a slow roll of thunder. Sometimes it is more abrupt, a sharp crack or a boom, as if something large has struck the ground nearby. In some cases, particularly with very shallow earthquakes, people report hearing a kind of hiss or roar moving through the earth just before the shaking begins. These sounds are not imagined. They are real, physical phenomena, the acoustic expression of seismic energy coupling into the air and entering the ear as well as being felt through the body. Animals seem particularly sensitive to this acoustic component, which may partly explain the long-observed behavior of animals acting strangely in the moments before a significant earthquake arrives. And sometimes, the shaking reaches far beyond what seems possible. The New Madrid earthquakes of 1811 and 1812, centered in what is now the central United States, were felt across an area of nearly 1 million square miles. The ground shook as far away as the East Coast. Church bells reportedly rang on their own in Boston and Washington, hundreds of miles from the epicenter. The Great Lisbon earthquake of 1755 sent seismic waves across Europe and triggered seiches, unusual oscillations of water, in lakes as far away as Scandinavia. The 2011 Tohoku earthquake in Japan was detected by seismographs on every continent, its energy rippling through the entire planet like a struck bell, echoing through the deep rock for days afterward. The Earth, in those moments, vibrates as a whole. Every seismograph on every continent registers the passage of the waves. Scientists can trace the energy as it bends and reflects through different layers of the interior, using those readings to map structures deep underground that no drill has ever reached. In a very real sense, major earthquakes are one of the primary ways we have learned what the inside of our planet actually looks like. The shaking you feel during an earthquake is not random chaos. It is the orderly, if violent, propagation of energy through rock, energy that follows physical laws, that can be measured and modeled and, to some degree, anticipated. Each wave type carries information. Each frequency tells a story. Each arrival time at a distant seismograph is a data point and an ongoing portrait of a living, dynamic planet. The ground beneath you is never quite as still as it seems. There is a phenomenon that most people never hear about, and yet it is one of the most remarkable things our planet does. After a truly great earthquake, one of the largest the world has ever recorded, the Earth does not simply shake and go still. It continues to move. Not in the chaotic, violent way of the initial rupture, but in something far more subtle and strangely beautiful. The planet begins to ring, like an enormous bell that has been struck. Seismologists call this free oscillation. The energy from a massive earthquake sets the entire Earth vibrating at its own natural frequencies, slow, deep pulsations that cause the planet to expand and contract, to twist slightly and then untwist, to deform in patterns that involve the whole globe at once. These oscillations have periods measured not in seconds but in minutes. Some of the longest last nearly an hour for each complete cycle. And they can continue for days, gradually fading as the energy slowly dissipates into heat deep within the rock. This is not a theoretical concept. It has been measured directly. After the 1960 Chilean earthquake, still the most powerful ever recorded, seismographs around the world detected the Earth oscillating for nearly 2 weeks. After the 2004 Sumatran earthquake, the same phenomenon was observed, the planet humming at frequencies far too low for any human ear to detect, but perfectly legible to sensitive instruments. In a very literal sense, the Earth was singing. And the waves from those great earthquakes do not simply spread outward from the epicenter and then fade quietly at the edges of the planet. They travel all the way around the world. Seismic waves from a major earthquake will cross entire ocean basins, pass through continental interiors, refract and reflect off the boundaries between different layers deep within the Earth, and eventually return to the point they started from, and then continue onward again. In the hours after a great earthquake, seismographs in distant countries record not just the first arrival of the waves, but second arrivals, and third arrivals, the same energy having traveled once around the planet and come back again. It is one of the most vivid reminders that the Earth is not just a backdrop to our lives. It is a physical object, a sphere of rock and metal with its own resonant properties, its own internal structure, its own response to force. And we have learned an enormous amount about what lies inside it simply by listening to those waves. But understanding what the waves tell us about an earthquake's size, its strength, its energy, its potential for destruction, required a different kind of science altogether. It required measurement. And the story of how we measure earthquakes is, in its own way, as interesting as the earthquakes themselves. For most of human history, there was no standard way to describe how large an earthquake was. People recorded them in diaries and official documents, noted the damage, described the duration of the shaking, compared them vaguely to other earthquakes they had experienced. Some early attempts at classification focused on the effects: how many buildings fell, whether the ground cracked, whether people were knocked off their feet. These descriptions were useful, but they were inherently local, shaped by where the observer happened to be standing and what kinds of structures happened to surround them. What scientists wanted was a way to measure the earthquake itself, not its effects in a particular place, but the actual energy released at the source. The first widely adopted attempt to do this came in 1935, when a seismologist at the California Institute of Technology named Charles Richter developed what he called a magnitude scale. Richter's scale was elegant in its simplicity. It used the amplitude of the seismic waves recorded on a specific type of seismograph at a specific distance from the earthquake, and it expressed the result as a single number. The larger the number, the larger the earthquake. His scale quickly became famous, perhaps too famous, in the sense that most people today still refer to any earthquake measurement as being on the Richter scale, even when it is not. The truth is that the Richter scale has largely been retired from scientific use. It had real limitations. It worked best for moderate earthquakes at specific distances, and it became less reliable for very large or very distant events. Over the following decades, seismologists developed a series of improved scales, culminating in what is now the standard used by scientists worldwide, the moment magnitude scale, abbreviated as MW. The moment magnitude scale measures something called seismic moment, a value that accounts for the area of the fault that ruptured, the average amount of slip along that fault, and the rigidity of the rock involved. It captures the physical reality of the earthquake more completely than any earlier scale. And crucially, it works reliably across the full range of earthquake sizes, from tiny tremors to the most powerful events ever recorded. What both the Richter scale and the moment magnitude scale share is a mathematical property that is easy to misunderstand but absolutely essential for interpreting earthquake measurements correctly. They are both logarithmic scales. In a linear scale, the kind most of us use every day, each step represents the same increase. Going from 3 to 4 adds 1. Going from 4 to 5 adds 1 more. But in a logarithmic scale, each step represents a multiplication. On the moment magnitude scale, each whole number increase corresponds to approximately 10 times greater ground motion, and roughly 32 times more energy released. This means the difference between a magnitude 3 and a magnitude 4 earthquake is not a modest increase. A magnitude 4 releases about 32 times more energy than a magnitude 3. A magnitude 5 releases 32 times more than a 4. By the time you reach a magnitude 7, you are talking about an event that releases millions of times more energy than the barely perceptible tremors that seismographs detect hundreds of times each day. The categories that seismologists use reflect this enormous range. Earthquakes below about magnitude 2 are microearthquakes, essentially imperceptible to humans, detected only by instruments. From magnitude 2 to roughly 3.5, they are minor, sometimes felt but rarely causing any concern. Magnitude 4 events are light earthquakes, widely felt but generally causing little damage. Magnitude 5 events are moderate, capable of causing damage to poorly constructed buildings. Magnitude 6 events are strong, potentially destructive near populated areas. Magnitude 7 earthquakes are major events capable of widespread and serious damage across large regions. And beyond magnitude 8, we enter the territory of great earthquakes, events capable of devastating entire countries, triggering tsunamis, and reshaping coastlines. The largest earthquake ever recorded was the 1960 Valdivia earthquake in Chile, which reached a magnitude of approximately 9.5. The energy released in that single event was estimated to be greater than all the earthquakes in the preceding quarter century combined. But here is something important to hold on to. Magnitude, for all its usefulness, tells you only part of the story. It tells you how much energy was released. It does not tell you how much damage resulted. And those two things can diverge dramatically. A magnitude 6.7 earthquake beneath a dense, modern city with shallow soil conditions can be catastrophically destructive. A magnitude 7.5 earthquake beneath a remote, lightly populated region with solid bedrock may cause relatively little harm to human infrastructure, even though it released far more energy. The relationship between earthquake size and earthquake damage is shaped by dozens of additional factors, and magnitude alone captures none of them. Depth plays a major role, as we have already touched on. The distance from populated areas matters enormously. The type of soil or rock underlying a region can amplify or dampen shaking significantly. Soft, water-saturated sediments tend to shake much more intensely and for much longer than hard bedrock, a phenomenon known as site amplification. The quality of building construction, the density of population, the time of day the earthquake strikes, all of these factors influence the human and physical impact in ways that a single magnitude number cannot express. This is why scientists use a separate system to describe not the source of an earthquake but its effects at different locations. That system is called seismic intensity, and it is measured not by instruments at the epicenter but by observations across the affected region. The most widely used intensity scale is the modified Mercalli intensity scale, which runs from Roman numeral I, detected only by instruments, through 12, total destruction. At level 4, indoor objects sway, dishes rattle, people awake or startled. At level 6, furniture moves, plaster cracks, walking becomes difficult. At level 9, buildings shift off their foundations, ground cracks, underground pipes break. Each level corresponds to a description of observed effects, gathered from reports by people across the region. When scientists collect intensity reports from across a broad area and map them visually, something revealing emerges. The resulting shake map, a color-coded representation of shaking intensity across a region, rarely looks like a simple circle spreading outward from the epicenter. It is irregular, shaped by local geology, by the direction the fault ruptured, by the depth and character of the source. Some areas far from the epicenter may have shaken more violently than areas much closer, because of the type of soil they rest on. Other areas close to the fault may have been partly shielded by the geometry of the rupture. The map tells a story that magnitude alone never could. So how often does all of this actually happen? The answer is, far more often than almost anyone realizes. The Earth is seismically active to a degree that most people never appreciate, because most of that activity is entirely invisible to ordinary human experience. Global seismic networks, which monitor the planet continuously from thousands of stations, detect somewhere in the range of 500,000 to over 1 million seismic events every year. That works out to roughly 1 earthquake somewhere on Earth approximately every 30 seconds, on average, when you include everything down to the smallest detectable tremors. The vast majority of these are tiny, micro-earthquakes and minor events that cause no shaking a person would ever notice. Somewhere between 15 and 20,000 events per year reach magnitude 4 or above, moderate enough to be felt by people nearby, though not necessarily causing damage. Major earthquakes of magnitude 7 or above occur roughly 15 to 20 times each year, on average. Great earthquakes above magnitude 8 happen once or twice a year, globally. When you absorb those numbers, the planet starts to feel different. Not frightening, exactly, but alive in a way that the stillness of daily life tends to conceal. Somewhere in the world right now, as you listen to this, the ground is moving. A fault is slipping somewhere. Seismic waves are traveling through the crust, through the mantle, through the deep interior of the Earth. Seismographs on every continent are recording the passage of energy that originated in a rupture you will never hear about. The Earth does not rest. It adjusts, and releases, and hums, quietly, constantly, beneath everything. On any given day, the Earth experiences roughly 500,000 seismic events. That number is almost impossible to hold in the mind at first. 500,000. In a single day. And yet, for the overwhelming majority of people on the planet, that day passes without the slightest sense that anything unusual is occurring beneath their feet. No trembling. No rattling windows. No reason to pause. The Earth is extraordinarily busy in ways that are simply invisible to us. Most of those events are so small that no human body could detect them under any circumstances. They register only on sensitive instruments, seismographs specifically designed to pick up the faintest whispers of ground motion. A magnitude 1 earthquake releases roughly the same energy as a small amount of industrial explosives. A magnitude 2 is barely stronger. These are events that happen constantly, in enormous numbers, all over the world, and they pass through the rock like quiet thoughts, noticed only by machines. Even as you move up the scale, the threshold for causing real harm remains surprisingly high. Earthquakes below about magnitude 4 are widely felt in their immediate vicinity. Dishes might shift, windows might rattle, a person sitting quietly might feel a brief, puzzling vibration, but they almost never cause structural damage. They are startling, occasionally, but not dangerous. The Earth shrugs, and life continues. On average, something in the range of 50 detectable earthquakes occur somewhere on Earth each day. 50 events that seismologists note, catalog, and add to their growing global record. But the vast majority of those, too, are small. They are felt locally, logged scientifically, and then forgotten by everyone except the people whose instruments recorded them. What emerges from all of this data, when you look at it across years and decades, is a pattern. A remarkably consistent, mathematically elegant pattern. For every increase of 1 unit in magnitude, the number of earthquakes drops by a factor of roughly 10. There are about 10 times as many magnitude 3 earthquakes as magnitude 4 earthquakes. About 10 times as many magnitude 4s as 5s. And so on, in both directions, scaling upward and downward with surprising regularity. This relationship is known as the Gutenberg-Richter law, named for the 2 seismologists who first described it in the 1940s. It applies not just globally but locally. In almost any seismically active region you examine, the same pattern holds. Many small events. Fewer medium ones. Very few large ones. And at the top of the scale, the truly great earthquakes, occurring so rarely that a single human lifetime might pass without witnessing one. Worldwide, roughly 130 earthquakes of magnitude 6 or above occur in an average year. Magnitude 6 events are strong enough to cause significant damage to poorly constructed buildings, particularly near the epicenter. At magnitude 7, widespread destruction becomes possible across a broad region. These are the earthquakes that make international news, that trigger emergency response systems, that leave lasting marks on landscapes and communities. And they happen, globally, about 15 to 20 times per year. Above magnitude 8, events are rare but not vanishingly so. A handful occur each decade. Magnitude 9 events are extremely uncommon, only a small number have been recorded since modern seismic networks were established in the early 20th century. The 1964 Alaska earthquake, the 2004 Sumatran earthquake, the 2011 Tohoku earthquake, these sit among the most powerful ever measured. And then there is the question of the upper limit. How large can an earthquake actually get? This is something scientists have thought carefully about, and the answer involves the physics of faults themselves. An earthquake's magnitude is determined partly by how large an area of fault ruptures and how much that fault slips. There are physical constraints on both. Fault zones on Earth are only so long, only so geometrically capable of producing a single coherent rupture. The largest subduction zone earthquakes, where one tectonic plate dives beneath another along an enormous, gently sloping surface, are capable of the greatest magnitudes precisely because those fault surfaces are so vast. But even they have limits. Most seismologists believe the practical upper ceiling for earthquakes on Earth sits somewhere around magnitude 10, and possibly lower. The 9.5 event in Chile in 1960 may be close to the largest our planet's fault geometry can produce. There is something quietly reassuring about that, the knowledge that as powerful as earthquakes are, the physics of the Earth itself places boundaries on how powerful they can become. Now, all of these events, the millions of small ones and the handful of great ones, are not distributed evenly around the globe. Earthquake activity is concentrated in specific regions, tied directly to the boundaries between tectonic plates. And no region on Earth concentrates that activity more dramatically than the one known as the Ring of Fire. The Ring of Fire is a vast arc of seismic and volcanic activity that traces the edges of the Pacific Ocean, running from the southern tip of South America up along the western coast of the Americas, continuing through Alaska and the Aleutian Islands, sweeping down through Japan and the Philippines and Indonesia, and eventually curving around toward New Zealand. It follows, almost precisely, the boundaries where Pacific tectonic plate meets the plates surrounding it, boundaries where oceanic crust is being driven beneath continental crust in a process of almost unimaginable slow-motion collision. The numbers associated with the Ring of Fire are striking. Approximately 90% of all earthquakes on Earth occur within or near this belt. About 80% of the world's largest earthquakes happen there. The countries and regions that sit along its length, Japan, Indonesia, Chile, Peru, the western United States, Alaska, experience seismic activity as a persistent, defining feature of daily life. This is not a coincidence of geography. It is a direct consequence of plate tectonics. The Pacific plate is large, old, and dense, and it is being subducted, pushed downward, beneath surrounding plates along nearly its entire perimeter. That subduction generates friction. Friction generates stress. Stress, accumulated over years and decades and centuries, eventually releases as earthquakes. The Ring of Fire is not a fixed, permanent feature in any cosmic sense. It is simply where the physics of the current configuration of plates has concentrated the most active boundaries. And within that ring, certain zones stand out even further, regions where the geometry of the plates, the speed of their movement, and the depth of the subduction combine to produce earthquakes with unusual frequency and power. Japan sits at one of the most complex of these intersections, where four tectonic plates meet in a relatively small area. Indonesia straddles another. The coastline of South America marks a third, where the Nazca Plate dives steadily eastward beneath the continent, building the Andes and periodically releasing enormous seismic energy along its length. The Earth's seismicity, seen from above, is not random. It is a map of forces, a portrait of boundaries, a record of the planet's ongoing effort to accommodate the motion of its broken, restless surface. And most of the time, it does so quietly, in the hundreds of thousands of small, unnoticed adjustments that occur each day, the vast and hidden labor of a living world. Every seismically active region on Earth has its own character. The way earthquakes behave in one part of the world, how deep they tend to be, how frequently they occur, how large they typically grow, what kind of faulting produces them, reflects the specific tectonic setting of that region. The earthquakes beneath the mountains of the Himalayas are different in nature from those along the coast of Chile. The tremors that ripple through the seafloor of the mid-Atlantic differ fundamentally from the great subduction zone ruptures of the Pacific. Geology is local in this way. The forces are global, but their expression is shaped by the particular geometry of each place. To appreciate this, it helps to look at where earthquakes are not, because the absences are just as telling as the concentrations. Consider Antarctica. The southernmost continent sits on its own tectonic plate, largely insulated from the active boundaries that drive seismicity elsewhere. It is, by the standards of most of the planet, remarkably quiet. Earthquakes do occur there, no part of the Earth is entirely free of them, but they are infrequent, generally small, and often associated with a very different kind of stress than tectonic collision. Some Antarctic earthquakes are thought to be caused by the movement and shifting of the ice sheet itself, enormous masses of glacial ice exerting and relieving pressure on the rock beneath. Others occur along the margins of the continent where the plate boundary is distant but not entirely absent. But compared to the seismic landscapes of Japan or Chile or Indonesia, Antarctica is very nearly still. This quietness is part of a broader pattern. The southern hemisphere as a whole is considerably less seismically active than the northern hemisphere, and this comes down to simple geography. The southern hemisphere contains far more ocean and far less continental landmass. Tectonic plate boundaries, while they certainly exist in the south, the mid-ocean ridges, the subduction zones along South America's western edge, the complex tectonics around New Zealand, are fewer and in many cases less geologically dramatic than the crowded, colliding boundaries of the northern hemisphere. The deep interior of the Southern Ocean is not a place where continents are pressing against one another. It is, relatively speaking, a place where the Earth exhales. There is another subtle factor worth noting. The gravitational pull of the Sun and Moon, the same forces that drive the ocean tides, exerts a tiny but measurable influence on the Earth's crust, causing it to flex very slightly as the tidal forces change. This tidal loading has been shown in some studies to have a weak but real correlation with earthquake timing in certain regions, particularly near coastlines and mid-ocean ridges. The effect is small, and it is certainly not a reliable predictor of individual earthquakes. But it is a reminder that even the Earth's seismicity is not entirely divorced from the larger gravitational dynamics of our solar system. The planet is responding, however faintly, to forces that originate far beyond its surface. Meanwhile, at the opposite extreme from Antarctica's quiet, there are regions where the ground barely seems to rest at all. Alaska is one of them. Few places on Earth have a seismic history as dramatic as the state of Alaska. It sits at the northern arc of the Pacific Ring of Fire, where the Pacific Plate drives northward and downward beneath the North American Plate at a relatively rapid pace. The result is one of the most tectonically active environments on the planet. Alaska experiences more large earthquakes than any other state in the United States, and it is not particularly close. Roughly 3 of the 10 most powerful earthquakes ever recorded in American history occurred in Alaska. The state accounts for the majority of all seismic energy released within the United States in any given year. The 1964 Great Alaska Earthquake stands as the most vivid expression of this. Occurring on Good Friday of that year, it reached a magnitude of 9.2, the most powerful earthquake ever recorded in North America, and the second most powerful ever recorded anywhere on Earth at the time of its occurrence. The rupture extended for approximately 800 kilometers. The ground near the epicenter was displaced both vertically and horizontally by extraordinary distances. Entire sections of coastline were permanently raised or dropped. Landslides buried neighborhoods. A tsunami radiated outward across the Pacific, causing death and destruction as far away as California and Hawaii. The shaking lasted for over 4 minutes, an almost incomprehensible duration for something so violent. Alaskan earthquakes are frequent in addition to being large. Moderate events, magnitude 5 and above, occur regularly throughout the year. The population is relatively sparse by global standards, which limits the human toll of many of these events, but the geological reality is constant and unmistakable. People who live in Alaska develop an intuitive familiarity with the ground moving beneath them that residents of most other places never acquire. But if Alaska holds the record for raw seismic power within the United States, another country holds the record for the sheer number of earthquakes recorded worldwide. Japan logs more earthquakes each year than almost any other nation on Earth. This is partly a consequence of geography. Japan sits at one of the most tectonically complex locations on the planet, where not 2 but 4 tectonic plates converge: the Pacific Plate, the Philippine Sea Plate, the Eurasian Plate, and the North American Plate. The boundaries between these plates run through and around the Japanese archipelago, creating multiple active fault systems operating simultaneously. It is, in the most literal sense, a country built on seismic instability. Japan also has one of the densest seismic monitoring networks in the world. The country's history of devastating earthquakes, from the Great Kanto earthquake of 1923, which killed over 100,000 people in Tokyo and Yokohama, to the Kobe earthquake of 1995, to the catastrophic Tohoku earthquake and tsunami of 2011, has driven investment in seismological infrastructure that is second to none. Japan detects and records earthquakes that would go unnoticed in less instrumented countries. The density of its monitoring network means that even very small events are captured, which inflates its recorded earthquake totals relative to countries with fewer stations. The result is a nation that lives in a kind of ongoing, intimate negotiation with seismic risk. Earthquake preparedness is woven into the fabric of Japanese society in ways that are genuinely remarkable, from the design of buildings and infrastructure to the education of children, the conduct of regular drills, and the development of early warning systems that can send alerts to millions of people within seconds of a rupture beginning. sometimes providing precious moments of warning before the strongest shaking arrives. Across the Pacific, Southern California presents its own distinctive seismic personality. The region experiences roughly 10,000 earthquakes per year, a figure that sounds alarming until you recognize that the overwhelming majority are far too small to feel. The seismicity of Southern California reflects the complexity of the fault systems threading through the region, not just the Great San Andreas, but dozens of secondary faults running at various angles, some of them capable of producing damaging earthquakes in their own right. The Los Angeles Basin sits within a region where the tectonic setting produces what geologists call blind thrust faults, faults that do not break the surface at all, hidden entirely beneath layers of sediment and older rock, their existence revealed only by the earthquakes they produce and the slow, subtle upward warping of the ground above them. The 1994 Northridge earthquake, which killed dozens of people and caused tens of billions of dollars in damage to the Los Angeles area, was produced by exactly this kind of hidden fault. No surface rupture. No visible crack in the ground. Just sudden, violent movement along a fault that, in many ways, the geological community had not fully anticipated. The seismic character of Southern California is shaped not just by the faults themselves but by the geology of the basins, deep accumulations of soft sediment that can significantly amplify seismic shaking, in some cases causing ground motion to be several times more intense than it would be on bedrock nearby. This is one of the reasons earthquake risk in the Los Angeles area remains a serious and ongoing concern despite major advances in building codes and construction practices. And yet the story of American seismicity does not end on the West Coast. There is a seismic zone in the interior of the continent that carries its own profound and often underappreciated history, and it sits not near a plate boundary but far from one, in one of the most geologically unexpected locations imaginable. The New Madrid seismic zone lies in the central United States, spanning parts of Missouri, Arkansas, Tennessee, Kentucky, Illinois, and Indiana. It takes its name from the town of New Madrid, Missouri, which stood near the epicenters of a remarkable series of earthquakes that struck during the winter of 1811 and 1812. Those earthquakes, occurring in a sequence over several months, are believed to have been among the largest to strike North America in recorded history. Some estimates place the largest of them at magnitude 8 or higher, though the uncertainties are considerable given the limitations of historical accounts and the absence of modern instrumentation. The effects were dramatic and far-reaching. The Mississippi River reportedly ran backward for a time, the result of ground deformation so severe that the flow of the river was temporarily reversed. New lakes were created where none had existed. Forests were toppled. Church bells rang in cities hundreds of miles away. The shaking was felt across an area encompassing more than 1 million square miles. What makes the New Madrid seismic zone scientifically fascinating, and from a risk perspective, sobering, is precisely its location. It is not at a plate boundary. It sits deep within the stable interior of the North American continent, far from the edges where tectonic plates interact. The forces that drive its earthquakes are thought to be related to ancient rifting, a failed attempt, hundreds of millions of years ago, for the continent to split apart along what is now the Mississippi embayment. That ancient scar in the crust has never fully healed, and the stresses within the continental interior continue to reactivate it. Because it sits in the continental interior, the New Madrid zone has geological properties that make large earthquakes there particularly far-reaching. The old, cold, rigid rock of the continental interior transmits seismic energy more efficiently than the younger, more fractured crust of the west coast. A large New Madrid earthquake would shake an area several times larger than a comparable event in California. Cities like Memphis, St. Louis, and even parts of the southeast would face significant shaking from a major New Madrid rupture, and many of the buildings in those cities were constructed at a time when Midwestern seismic risk was not taken seriously by engineers or planners. The zone remains active today. Small to moderate earthquakes occur there regularly, too small to feel in most cases but faithfully recorded by the seismographs that now monitor the region. The big events, the kind the winter of 1811 brought, have not returned in recorded history since then. But geologists believe they will, eventually, as they have many times before in the deeper geological past. The continents hold their earthquakes in places you might never expect. Plate boundaries are where the drama is loudest, but they are not where it ends. The Earth's seismic life runs deeper and wider than any single line on a map. Pakistan sits at one of the most geologically intense convergence zones on Earth. To understand why, you have to think about the slow, immense collision that has been unfolding for tens of millions of years between the Indian subcontinent and the Eurasian landmass. The Indian plate has been moving northward for a very long time, pressing steadily into Asia with a force measured not in anything human but in the accumulated momentum of an entire tectonic plate in motion. The result of that collision is visible in the most dramatic way imaginable. The Himalayas, the highest mountain range on Earth, pushed upward by the ongoing compression of two continental masses refusing to subduct cleanly beneath one another. Pakistan lies directly within the western arm of this collision zone. The country sits at a place where the Arabian Plate, the Indian Plate, and the Eurasian Plate all interact in close proximity, creating a tectonic environment of extraordinary complexity. Major fault systems run through the country in multiple directions. The Chaman Fault System in the west accommodates much of the lateral motion between the Indian and Eurasian plates. The Makran subduction zone traces the southern coast, where the Arabian Sea floor is being driven beneath the Iranian and Pakistani landmass. And throughout the north and northwest, the deeply crumpled, folded terrain of the mountain ranges records in its very structure the ongoing, unresolved compression of two continents in slow collision. What this means in practical terms is that Pakistan experiences significant earthquakes with genuine regularity, and that many of those earthquakes carry a particular quality that makes them especially dangerous. They are shallow. Depth, as we have discussed, shapes the character of an earthquake's impact profoundly. A deep earthquake, one originating 50 or 100 miles beneath the surface, releases its energy far from the ground where people live. By the time those waves travel upward and outward to the surface, they have spread across a wider area, and the intensity of shaking in any one location is moderated by that spreading. A shallow earthquake is different in a fundamental way. When the rupture begins only a few miles down, sometimes less than 10 kilometers, the energy does not have far to travel. It arrives at the surface concentrated, abrupt, and intense. The shaking is sharper. The ground motion is more violent. The potential for damage in the immediate area of the rupture is dramatically higher. Many of Pakistan's most devastating historical earthquakes have been shallow in precisely this sense. The 2005 Kashmir earthquake, which struck the northern regions of Pakistan and Kashmir with a magnitude of 7.6, originated at a relatively shallow depth and caused destruction of almost incomprehensible scale. Over 70,000 people were killed. Entire towns and villages in the mountainous terrain were obliterated, their buildings, many of them constructed with heavy stone and unreinforced masonry, simply unable to withstand the violent, close-range shaking. The topography of the region compounded the disaster. Massive landslides swept down the steep mountain slopes, burying roads and blocking valleys. The remoteness of the affected areas made rescue and relief efforts agonizingly difficult. Hundreds of thousands of people were left homeless as winter approached. The vulnerability of Pakistan's built environment to seismic shaking is a recurring theme in the country's earthquake history, and it reflects a challenge faced by many nations in geologically active regions. Construction in mountainous and rural areas often relies on traditional methods and materials that perform very poorly during strong ground motion. Heavy roofs, thick stone walls, unreinforced brick, these are materials that collapse readily when the ground moves rapidly and unexpectedly. The gap between what buildings experience during a major shallow earthquake and what they are capable of withstanding is, in too many places, enormous. And yet the geological reality of Pakistan's position is not going to change. The Indian plate will continue pressing northward. The faults threading through the country will continue accumulating stress. The question, as with so many seismically active nations, is not whether large earthquakes will occur, but how prepared the communities in their path will be when they do. The earthquakes that strike Pakistan arise from the grand, slow collision of tectonic plates, forces operating at the largest scales of planetary geology. But earthquakes are not always products of such grand and ancient forces. Sometimes they arise from sources that are far more surprising, far more human. It has been known for decades that human activities can, under certain circumstances, trigger earthquakes. The mechanisms vary, but the underlying principle is consistent. If the crust in a given area is already stressed, already holding accumulated strain close to the threshold of failure, then it may not take much to push it over that threshold. A relatively small perturbation in the local stress field can be enough to initiate a rupture that might otherwise have occurred naturally, perhaps much later. One of the most well-documented examples involves the injection of fluids into the ground. When water or other fluids are pumped into deep rock formations, whether as part of oil and gas operations, geothermal energy projects, or wastewater disposal, they can increase pore pressure within the rock. Elevated pore pressure effectively reduces the friction holding fault surfaces together, lowering the stress required to trigger slip. In areas where such injection has occurred near pre-existing faults, the correlation with increased seismic activity has been documented in numerous studies and is now broadly accepted within the seismological community. The earthquakes produced by these activities are, in most documented cases, relatively small, typically in the range of magnitude 2 to 4. Occasionally they are larger. A small number of events linked to fluid injection have reached magnitude 5 or above, large enough to cause minor damage and significant public concern. But the majority are events that would not ordinarily attract attention, tremors that fade quickly and leave no mark beyond an entry in a seismic catalog. Volcanoes add another layer to this picture. Volcanic systems are seismically active in their own right, generating earthquakes through a variety of mechanisms: the movement of magma through rock, the pressurization of hydrothermal systems, the fracturing of rock by thermal stress, and the tectonic faulting that occurs in the broader volcanic region. Volcanoseismology has become an important tool for monitoring eruption potential, because the patterns of small earthquakes beneath a volcano can provide early warning that magma is moving upward through the crust. A sudden increase in shallow seismicity beneath a volcanic edifice is one of the signals that scientists watch most closely. What both of these phenomena, human-induced seismicity and volcanic seismicity, have in common is that they remind us earthquakes are not monolithic events arising from a single type of cause. They are the expression of stress release in rock, and stress can arise from many sources. Most natural earthquakes, however, do not arrive alone. When a significant earthquake occurs, it is rarely a singular, isolated event. It tends to come with companions, smaller earthquakes that follow the main shock, sometimes within minutes, sometimes over days or weeks or months. These aftershocks occur because the initial rupture reorganizes the stress field of the surrounding rock. Some areas that were previously held in stable equilibrium find themselves, after the main shock, pushed closer to failure. Others are relieved of stress and become quieter. The result is a cascade of adjustments, a geological settling in around the new configuration left by the main event. Aftershock sequences follow statistical patterns that seismologists have described mathematically. The largest aftershock in a sequence is typically about 1 magnitude unit smaller than the main shock, a rule of thumb known as Bethes' law. The rate of aftershocks decays over time according to a relationship called Maury's law, which describes how the frequency of aftershocks diminishes in a predictable way as the weeks and months pass. These patterns are reliable enough to be useful for probabilistic forecasting, giving scientists a framework for estimating how many aftershocks of various sizes are likely to follow a given main shock. But the influence of a large earthquake does not end with its immediate aftershock sequence. Large earthquakes can reach out and affect fault systems at considerable distances, sometimes at distances that seem almost impossibly remote from the original rupture. Static stress changes, the permanent redistribution of stress that results from fault slip, can affect areas tens to hundreds of kilometers from a main shock. If a large earthquake relieves stress along one segment of a fault, it may simultaneously increase stress at the ends of that segment, bringing neighboring fault sections closer to failure. This phenomenon, known as stress triggering, has been documented in multiple earthquake sequences around the world, and it is one of the reasons why a major earthquake in one part of a fault system can elevate the probability of future events on nearby faults. Even more remarkable is the evidence for dynamic triggering, the triggering of earthquakes by the passage of seismic waves themselves, at distances far beyond what static stress changes could explain. There are well-documented cases of large earthquakes triggering seismic activity thousands of kilometers away, far outside any region that could be affected by the static redistribution of stress. The mechanism appears to involve the transient stresses produced as surface waves pass through the crust, momentarily raising and lowering pore pressure in fluid-saturated rock, briefly nudging faults that were already close to failure. Perhaps most intriguingly, acoustic waves, sound waves traveling through the atmosphere or the shallow crust, have been shown in some studies to play a role in triggering aftershocks. The passage of infrasound, low-frequency sound below the threshold of human hearing, produced by a large earthquake and traveling outward through the atmosphere, can interact with the shallow crust in ways that appear to initiate small seismic events. It is a subtle and still somewhat debated phenomenon, but the evidence points toward a degree of interconnection between seismic and acoustic energy that was not widely appreciated until relatively recently. Not every seismic region expresses its activity in the familiar pattern of main shock followed by aftershocks. Some areas experience what seismologists call earthquake swarms, extended sequences of earthquakes in which no single event clearly dominates as a main shock. In a swarm, dozens or hundreds or even thousands of small to moderate earthquakes occur over days, weeks, or months in a relatively small area, without a single large event anchoring the sequence. Swarms are particularly common in volcanic regions, where the movement of fluids and magma can sustain seismic activity over extended periods without producing a single catastrophic rupture. They also occur in some geothermal areas and in regions where fluid migration through the crust drives ongoing seismicity. The character of a swarm is different from a main shock aftershock sequence in ways that are not merely statistical. It creates a different experience for the people who live through it, a persistent, unsettling awareness that the ground is frequently restless, without the relative reassurance that comes from knowing a large event has already occurred and the activity is gradually declining. Swarms can be difficult to interpret in real time, because they do not always remain small. Occasionally what begins as a swarm culminates in a significant earthquake, which then retrospectively looks like a foreshock sequence. The distinction between a swarm and a foreshock sequence is often only clear in hindsight. Then there are the regions that go quiet for a very long time, sometimes centuries, before breaking loose with sudden and catastrophic force. Seismic gaps are stretches of active fault zones that have not produced a major earthquake in a historically long time. They are regions where stress is presumably accumulating, where the fault is locked, where the geological evidence suggests significant earthquakes have occurred in the past and will occur again. Some seismic gaps are well known and closely monitored. Others sit in regions with limited historical records, where the absence of documented earthquakes may reflect not genuine seismic quietude but simply the absence of people keeping records. The challenge with seismic gaps is that the silence itself carries no information about when the next event will occur. A fault that has been quiet for 200 years may be close to failure, or it may remain locked for another 200 years. The geological clock does not announce its intentions. Scientists can estimate the average recurrence interval of large earthquakes on a given fault, based on the geological record of past ruptures preserved in trenches and cores, but the variability around those averages is considerable, and the uncertainty grows the further you try to project into the future. There is a beautiful and slightly humbling quality to this uncertainty. The Earth operates on timescales that dwarf human history. The geological record extends back millions of years. Our written records of earthquakes extend back only a few thousand, and reliable instrumental records only a little over a century. We are, in a very real sense, trying to understand a long and complex story from a very short passage of text. And woven through all of this, through the aftershocks and the swarms and the seismic gaps and the distant triggering, is a thread of influence so subtle that it was long considered negligible, until careful analysis of global seismic data began to suggest otherwise. The Earth has tides. Not just in its oceans, but in its solid body. As the gravitational pull of the moon and sun shifts relative to any point on Earth's surface, the crust itself flexes very slightly, rising and falling by amounts measured in centimeters over the course of a day. This solid Earth tide is real and measurable, and it exerts a tiny, periodic stress on the crust and the faults within it. For large earthquakes, the effect of this tidal stress appears to be negligible. The stresses involved are simply too small relative to the forces that drive major fault ruptures. But for very small earthquakes, microearthquakes occurring on faults that are already critically stressed, the statistical evidence suggests a weak but detectable correlation with tidal phase. In some studies, small earthquakes in certain regions occur slightly more often when the tidal stress is oriented in a way that promotes fault slip, and slightly less often when it is not. The effect is subtle. It is not large enough to be useful for earthquake prediction in any practical sense. But its existence is philosophically interesting. It means that even the rhythms of the moon, the same gravitational force that pulls the oceans into their tides, that sailors have read for thousands of years, leaves its faint fingerprint on the seismicity of our planet. The Earth is responsive to the plates pressing against one another across geological time, to the fluids moving through its pores and fractures, to the passage of waves from distant earthquakes, to the slow, reliable pull of the moon across the sky. Everything is connected, in ways that are just subtle enough to have taken us a very long time to notice. The ground beneath a city is not uniform. Walk a few blocks in almost any major urban area and you are crossing, without knowing it, from one geological substrate to another, from bedrock to ancient river sediment, from compacted gravel to soft bay mud laid down over thousands of years. These differences are invisible from the surface. They do not announce themselves. But when seismic waves arrive, those differences become suddenly, dramatically relevant. Soft sediments behave very differently from hard rock when seismic energy passes through them. In hard bedrock, seismic waves travel quickly and maintain much of their original character. In soft, water-saturated sediment, something else happens. The waves slow down as they enter the softer material, and because the energy carried by those waves must be conserved, the slowing translates into an increase in amplitude. The ground shakes more. It shakes longer. The seismic energy becomes concentrated in the soft layer, amplified in ways that can increase the intensity of shaking by factors of 2, 3, 5, or even more compared to nearby areas on solid rock. This phenomenon, site amplification, is one of the most important factors separating a damaging earthquake from a catastrophic one, and it is written into the geology of countless cities around the world. Mexico City offers one of the most vivid illustrations. Much of the city is built on the soft, compressible sediments of a former lake bed, the ancient Lake Texcoco, drained over centuries of colonial development. When the 1985 Michoacan earthquake struck, its epicenter was over 300 kilometers away on the Pacific coast. By rights, a city that far from the rupture might have expected moderate shaking. Instead, the soft lake sediments beneath Mexico City resonated with the incoming seismic waves like a bowl of jelly, amplifying the shaking to devastating levels. Hundreds of buildings collapsed. Thousands of people were killed. The epicenter was distant, but the geology of the city made it vulnerable in ways that the epicenter alone could never have predicted. San Francisco Bay contains similar soft bay mud deposits along much of its shoreline. During the 1989 Loma Prieta earthquake, it was the neighborhoods built on fill and soft sediment, particularly the Marina District, developed partly on rubble and fill placed after the 1906 earthquake, that suffered the most severe damage, while areas on bedrock nearby experienced the shaking as something far more manageable. The ground itself determined who was most at risk. But amplified shaking is only the beginning of what soft, saturated ground can do when a strong earthquake arrives. One of the most visually striking and geologically fascinating secondary effects of earthquake shaking is a process called liquefaction. It occurs when loose, water-saturated sand or silt is subjected to rapid, repeated shaking. Under those conditions, the water pressure between the grains of sediment rises suddenly, and the grains lose their frictional contact with one another. The solid ground effectively becomes a liquid, not dramatically, not like water, but enough that it loses its ability to support structures. Buildings tilt and sink. Underground pipes and tanks, being lighter than the surrounding soil, float upward. Roads buckle. The surface of the ground may erupt in fountains of water and sand as the pressurized water finds pathways upward through the liquefied layer. Liquefaction has been documented in earthquakes around the world and is responsible for some of the most surreal and enduring images in earthquake photography: apartment buildings tilted at steep angles, still structurally intact but resting at impossible angles in ground that softened beneath them. The 1964 Niigata earthquake in Japan produced dramatic liquefaction across broad areas of the city. The 2011 Christchurch earthquake in New Zealand caused widespread liquefaction throughout residential neighborhoods, forcing the abandonment of entire suburbs as the ground repeatedly failed to recover its bearing strength between aftershocks. Strong shaking does not stay confined to flat ground, either. In mountainous terrain, earthquakes routinely trigger landslides, sometimes on a massive scale. Slopes that had been stable for decades or centuries, held together by the friction and cohesion of the soil and rock, are destabilized in seconds by intense ground motion. The 1970 Ancash earthquake in Peru triggered a catastrophic debris avalanche from the slopes of Nevado Huascarán that buried the town of Yungay almost entirely, killing tens of thousands of people. In the 2005 Kashmir earthquake, landslides repeatedly severed the mountain roads that rescuers needed to reach affected communities, extending the suffering of the disaster far beyond the shaking itself. In cold, snowy mountain environments, the same violent shaking can trigger avalanches, sending enormous masses of snow and ice down slopes at speeds that leave no time for escape. The seismic shaking of 1970 contributed directly to avalanche conditions on Nevado Huascarán. More recently, the 2015 Nepal earthquake triggered a large avalanche on the slopes of Mount Everest, killing climbers at base camp who had survived the shaking itself. And then there is fire. Fire is one of the oldest and most destructive companions of large urban earthquakes, and it arises from a conjunction of physical realities that are almost difficult to prevent. Gas mains fracture. Electrical lines snap and arc against dry debris. Chemical storage facilities rupture. Open flames in homes and kitchens, stoves, heaters, candles, are knocked over in the chaos of violent shaking. Under ordinary circumstances, any of these ignition sources would result in a fire that could be quickly contained. But in the aftermath of a major earthquake, the conditions that allow fires to be contained are precisely the conditions that no longer exist. Water mains, running through the same ground that just experienced intense shaking, are often broken in multiple places. Fire hydrants may be dry or at reduced pressure. Emergency services are overwhelmed, responding to collapse rescues across a wide area. Road blockages from debris prevent fire trucks from reaching affected neighborhoods. And so fires that begin as small, containable blazes grow and merge and spread across neighborhoods of damaged buildings, consuming what the shaking left standing. The 1906 San Francisco earthquake is perhaps the most historically significant example of this dynamic. The earthquake itself caused widespread structural damage, but it was the fires that followed, burning for 3 days, consuming roughly half the city, that accounted for the majority of the total destruction. The fire was fed partly by broken gas mains and partly by a well-intentioned but ultimately catastrophic decision to use explosives to create fire breaks, which in several cases simply ignited new blazes in fresh locations. The Great Kanto earthquake of 1923, which struck the Tokyo-Yokohama region at lunchtime when cooking fires were burning in millions of homes, resulted in firestorms that killed far more people than the shaking itself. This leads to what is perhaps the most important and most consistently underappreciated truth about earthquake disasters. Most people who die in earthquakes do not die from the shaking. They die from buildings. The shaking itself, in the absence of structures, is rarely directly fatal. It knocks people off their feet. It can cause rockfalls. It can trigger liquefaction and landslides. But the primary mechanism of mass casualties in earthquakes, across history and across cultures, is the collapse of the built environment onto the people inside it. Walls fall. Roofs cave in. Buildings pancake. And the people who are sleeping or working or sheltering within them are crushed. This is not a subtle or secondary point. It is the central fact of earthquake mortality, and it has profound implications for how we think about seismic risk. An earthquake of a given magnitude striking a region of high quality, well-engineered construction may kill very few people. The same magnitude earthquake striking a region of unreinforced masonry, poorly constructed concrete, or traditional heavy roof building stock can kill thousands or tens of thousands or more. The 2010 Haiti earthquake had a magnitude of 7.0, a strong event, certainly, but not exceptional by global standards. It killed over 200,000 people. The following year, the Christchurch earthquake in New Zealand reached a magnitude of 6.3, smaller, and killed 185 people, almost all of them in a single building that collapsed during the lunch hour. Meanwhile, the 2011 Tohoku earthquake in Japan, with a magnitude of 9.0, among the most powerful ever recorded, killed roughly 16,000 people, the vast majority of whom died in the tsunami rather than building collapse. Japan's decades of investment in earthquake-resistant construction meant that many buildings, even in areas of severe shaking, did not fall. The numbers are stark, and their implication is clear. Earthquake risk is not primarily a geological problem. It is an engineering problem, a social problem, an economic problem. The geology determines where and how hard the ground shakes. The buildings determine whether people survive. Where an earthquake strikes matters just as much as how large it is. An identical earthquake striking a densely populated urban area and a remote, sparsely inhabited region will produce catastrophically different outcomes. This seems obvious when stated directly, but it is easy to lose sight of when focusing on magnitude numbers and fault maps. The overlap between seismic hazard, the physical probability of strong shaking, and human vulnerability, the density of population and the quality of the built environment, is what seismologists call seismic risk. And managing that risk requires thinking about both sides of the equation simultaneously. Some of the highest risk cities in the world sit precisely at the intersection of high seismic hazard and large populations in vulnerable buildings: Kathmandu, Karachi, Istanbul, Tehran, Manila. These are places where the geological setting is genuinely dangerous and where much of the building stock was constructed without adequate seismic resistance. The concern among earthquake scientists about these cities is significant and long-standing. And then there is the sea. When an earthquake occurs beneath the ocean floor, specifically when it involves the kind of vertical fault movement that displaces a large volume of water, it can generate one of the most dangerous natural phenomena on Earth. A tsunami begins not as a wall of water but as an almost invisible disturbance in the open ocean. The seafloor, suddenly displaced upward or downward along a fault, pushes the entire column of water above it. That displacement propagates outward as a series of very long waves, wavelengths that may span hundreds of kilometers from crest to crest. In the deep ocean, these waves travel at extraordinary speeds, sometimes exceeding 800 kilometers per hour, comparable to the cruising speed of a commercial aircraft. A person on a ship in the open ocean might barely notice their passage. The waves are long and gentle in deep water, and the sea surface rises and falls by only a meter or less as they pass. But as the waves approach shallow coastal waters, everything changes. The seafloor rises. The waves slow down. And as they slow, the energy they carry must go somewhere, so they grow. They pile up. What was a gentle swell in the deep ocean becomes a towering mass of moving water as it enters shallow coastal zones, sometimes reaching heights of 10, 20 or 30 meters before it strikes the coast. The 2004 Indian Ocean tsunami, generated by the Great Sumatran earthquake, sent waves across the entire Indian Ocean basin, killing over 200,000 people across more than a dozen countries. Communities in Sri Lanka, India, Thailand, the Maldives, and as far away as the coast of East Africa were struck by waves that arrived with little or no warning. The 2011 Tohoku tsunami in Japan, despite the country's extensive warning systems and seawall infrastructure, killed the majority of the earthquake's victims as waves overwhelmed coastal defenses and swept inland for distances that, in some areas, exceeded several kilometers. Tsunami generation is not guaranteed for every submarine earthquake. It requires a combination of factors. The earthquake must be large enough, the fault must involve sufficient vertical displacement, and the geometry of the seafloor and coastline must allow the energy to be efficiently transmitted toward populated shores. Strike-slip earthquakes, where the two sides of a fault slide horizontally past each other, generate little vertical seafloor displacement and therefore produce minimal tsunamis. But thrust earthquakes, where one plate is forced upward over another, can displace the seafloor dramatically, and it is precisely these earthquakes, common in subduction zones like those of the Pacific Ring of Fire, that pose the greatest tsunami risk. The effects of earthquake-generated water motion extend beyond the open coast. Bodies of water that are partially enclosed, bays, fjords, harbors, estuaries, can develop their own resonant sloshing response when seismic waves pass through them, a phenomenon known as a seiche. Unlike a tsunami, which arrives as a series of waves generated by seafloor displacement, a seiche is driven by the direct shaking of the water basin itself. The ground moves, the water sloshes back and forth within its container, and if the frequency of the shaking matches the natural resonant frequency of the basin, the oscillations can grow to significant amplitudes. Lake Geneva, in Switzerland, has historical records of seiches following distant earthquakes. Norwegian fjords have experienced seiches during Scandinavian earthquakes. In Alaska, the 1964 earthquake generated seiches in enclosed waterways far from the epicenter that were dramatic enough to overturn boats in flood low-lying areas. These are not minor curiosities. In the right geography, seiches can be genuinely dangerous. And the phenomenon scales all the way down to the domestic. People who have been in their homes during moderate earthquakes sometimes report the water in their swimming pools sloshing and splashing over the edges, water that continued moving for many seconds after the shaking stopped, rocking back and forth in its concrete basin, responding to the same physics that drives seiches in lakes and harbors, just at a scale that happens to be visible and familiar. The water in a swimming pool, rocking gently after an earthquake passes. The water in a bay, surging back and forth in a slow, powerful oscillation. The water of an ocean, crossed by an invisible wave traveling at the speed of a jet. All expressions of the same physical truth, that when the earth moves, everything resting on it and within it moves in response. The planet does not shake in isolation. It shakes everything. On the 22nd of May, 1960, the ground beneath southern Chile began to move in a way the world had never measured before and has not measured since. The earthquake that unfolded that afternoon along the Chilean coast was not simply large. It was in a category of its own, a rupture so vast, so sustained, and so energetic that it has retained, for over 6 decades, the title of the most powerful earthquake ever recorded in human history. Its magnitude was 9.5. The fault that slipped extended for nearly 1,000 kilometers along the subduction zone where the Nazca Plate dives beneath South America. The rupture lasted for approximately 10 minutes. The ground near the epicenter moved by several meters. The energy released was staggering, greater than the sum of every other earthquake in a typical year, combined. The immediate effects were devastating across southern Chile. Towns were flattened. Landslides swept down the Andes. Rivers were blocked. A new lake formed in the space of hours where none had existed before. But the earthquake did not keep its destruction local. The tsunami it generated crossed the entire Pacific Ocean, killing people in Hawaii, in Japan, and in the Philippines, traveling thousands of kilometers from its source, arriving at distant shores hours after the ground in Chile had stopped moving. In Hilo, Hawaii, waves reached heights of over 10 meters, sweeping through the city and killing 61 people. In Japan, nearly 10,000 kilometers from the epicenter, waves of up to 6 meters killed over 100 people and destroyed thousands of homes. The 1960 Chilean earthquake is a benchmark, a reference point against which every other seismic event is measured. It is the outermost edge of what the geological architecture of our planet appears capable of producing. But the consequences of truly great earthquakes are not limited to shaking and waves. They extend into domains that seem, at first, almost too abstract to be real. Large earthquakes can physically move cities. Not in a gradual, almost imperceptible way like the creeping of tectonic plates, but in sudden, measurable jumps. When a major fault ruptures, the land on either side of it shifts. In some cases, that shift is substantial enough to relocate a city's position on the globe by amounts that can be measured with precision. The 2010 Chile earthquake, magnitude 8.8, moved the city of Concepcion approximately 3 meters to the west. The 2011 Tohoku earthquake shifted parts of the Japanese coast as much as 5 meters eastward. The seafloor near the rupture zone dropped by several meters. These are not metaphors. They are surveyed, documented, measurable displacements of real places on the surface of the Earth. And the effects travel even deeper than the surface. An earthquake of sufficient magnitude can alter the distribution of mass within the Earth in subtle but real ways. Mass distribution determines how the planet spins. The Earth, like any rotating body, is subject to a principle from physics. If mass moves closer to the axis of rotation, the rotation speeds up. If mass moves away, it slows down. The same principle that causes a spinning figure skater to speed up when she draws her arms in. When a great earthquake redistributes mass within the crust and upper mantle, it can affect the length of the day. The effect is extraordinarily small. The 2011 Tohoku earthquake, for example, is estimated to have shortened the Earth's day by approximately 1.8 microseconds. A microsecond is 1/1,000,000th of a second. The change is real, but it is so small that no human could ever perceive it, and it has no practical consequence for daily life. What it represents, though, is something profound, a single geological event capable of changing the fundamental rotation rate of our entire planet. However slightly, however briefly. The same earthquake that shortened the day also shifted the Earth's axis slightly, not the geographic poles, but the axis around which mass is distributed, known as the figure axis. Again, the shift was tiny, measured in centimeters. But it was real. The planet's orientation in space was measurably changed by the rupture of a fault zone off the coast of Japan. These effects are not unique to the Tohoku earthquake. The 2004 Sumatra earthquake also shortened the day, also shifted the figure axis. The 1960 Chilean earthquake did the same. Every great earthquake does, to some infinitesimal degree. The cumulative effect of all the earthquakes in Earth's history has contributed, in a small way, to the planet's current rotational state. And then there is the mountain. Mount Everest, the highest point on Earth's surface, changed after the 2015 Nepal earthquake. The earthquake, which struck with a magnitude of 7.8 and killed nearly 9,000 people across Nepal, India, and Tibet, caused measurable deformation of the Himalayan landscape. Satellite measurements in the months following the earthquake indicated that Everest had decreased in height by approximately 2.5 centimeters. The compression of the crust during the rupture, and the subsequent settling and relaxation of the terrain, produced a small but documented change in the elevation of the world's highest peak. The Himalayas themselves are, of course, the product of exactly this kind of tectonic process operating over millions of years. They rise because the Indian plate continues pressing northward into Asia, buckling and uplifting the crust between them. They also periodically shrink, locally and briefly, when earthquakes release accumulated stress and allow the compressed rock to partially relax. The mountain is not static. It breathes, imperceptibly, with the rhythms of the geology beneath it. The 1906 San Francisco earthquake belongs in any honest account of how seismic events shape human history, not only for its geological significance but for the way it changed the course of a city and contributed to the development of modern earthquake science. The earthquake struck in the early morning of April 18th, when most of the city was asleep. The rupture propagated along nearly 300 miles of the San Andreas Fault, producing violent shaking across the northern California coast. The shaking lasted for perhaps a minute. The damage was widespread and severe. But as we have noted, the shaking was not what ultimately defined the catastrophe. It was the fires that followed. Gas mains had been severed across the city. Water mains had been broken in hundreds of places, leaving the firefighting infrastructure without the water it needed. Over the next 3 days, fire consumed approximately 25,000 buildings across nearly 500 city blocks. The fires were fought with desperate creativity and limited success, using dynamite to create fire breaks, a strategy that worked in some areas and made things worse in others. By the time the fires were extinguished, roughly half of San Francisco had been destroyed. The death toll was at least 3,000, and likely higher, given the destruction of records and the tendency of early official accounts to understate the human cost. The 1906 earthquake and fire reshaped San Francisco in ways that are still visible in its urban geography. It also stimulated serious scientific investigation of the San Andreas Fault, leading to the foundational work of seismologist Harry Fielding Reid, who analyzed the displacement patterns around the fault and developed the elastic rebound theory, the framework that explains how stress builds and releases along faults, and which remains central to earthquake science today. Disaster, in this case, became the catalyst for understanding. The 2004 Indian Ocean earthquake and tsunami occupy a different place in collective memory, an event of such geographic scale and such human tragedy that it became a turning point in global awareness of tsunami risk. The earthquake began just after midnight on the morning of December 26, local time, off the northern coast of Sumatra. The rupture propagated northward along the subduction zone for over 1,000 kilometers, lasting between 8 and 10 minutes. The seafloor was thrust upward along the length of the rupture, displacing an enormous volume of ocean water and sending tsunami waves outward in all directions across the Indian Ocean. What followed over the next several hours was one of the most widespread natural disasters in recorded history. Waves struck the coast of Aceh, Indonesia, within minutes of the earthquake, no warning possible, the distance too short. 2 hours later, they struck Sri Lanka and the southeastern coast of India. 2.5 hours after the rupture, they reached Thailand's tourist coast, arriving as a sudden, strange withdrawal of the sea before the waves came. 7 hours after the earthquake, waves reached the coast of Somalia, 4,500 kilometers from the epicenter. The total death toll was estimated at between 200 and 230,000 people across 14 countries. It remains one of the deadliest natural disasters in modern history. And it exposed, with terrible clarity, the absence of a tsunami warning system in the Indian Ocean comparable to the one that had been operating in the Pacific since 1949. In the Pacific, the DART buoy network and international warning centers would have given coastal populations hours of warning for a wave originating thousands of kilometers away. In the Indian Ocean in December 2004, no equivalent system existed. People in Sri Lanka and India had over 2 hours between the earthquake and the wave's arrival, time that, with appropriate warnings, could have saved tens of thousands of lives. Within years of the disaster, an Indian Ocean tsunami warning system was established. The catastrophe, as so often happens, became the event that made the investment and prevention finally seem possible to justify. Pakistan's relationship with seismic disasters deserves acknowledgement in any account of earthquake consequences. Since 1950, earthquakes have killed over 83,000 people within the country's borders, a toll accumulated through dozens of events large and small across one of the world's most seismically active and geologically complex regions. The 2005 Kashmir earthquake alone accounted for the majority of that total. But the losses extend across decades in geography, from the Makran coast to the Hindu Kush to the plains of the Indus Valley. The number is not just a statistic. It represents the accumulating intersection of geological reality and human vulnerability, the cost of living in a tectonically active landscape with building traditions and economic constraints that have not always been able to keep pace with the seismic demands placed upon them. Understanding these events, not just experiencing them, not just surviving them, but genuinely understanding their physics, their patterns, their depths and durations and implications, requires instruments of extraordinary sensitivity and a global framework for sharing what those instruments detect. A modern seismometer is a remarkable piece of technology. At its core, the principle is deceptively simple. You suspend a mass so that it remains as still as possible while the frame around it moves with the ground. The relative motion between the stationary mass and the moving frame is what gets measured and recorded. In practice, achieving that suspension, making the mass genuinely inertial enough to remain still while the earth around it trembles, involves sophisticated engineering. Modern broadband seismometers can detect ground motion measured in nanometers. A nanometer is 1/1,000,000th of a meter. A strand of human DNA is about 2 nanometers wide. These instruments can detect the passage of seismic waves from earthquakes on the other side of the planet, the slow tidal deformation of the Earth's crust, the distant rumble of ocean waves interacting with the seafloor, and the faint signal of a nuclear test conducted thousands of kilometers away. The data from these instruments flows continuously, in real time, to seismic networks around the world. At the center of this global effort is the International Seismological Center, based in the United Kingdom, which serves as the primary archive for earthquake data from stations worldwide. It collects readings from hundreds of seismograph networks, analyzes and cross-references them, and produces a comprehensive catalog of seismic events that is used by researchers, governments, and hazard assessment agencies around the world. The global seismograph network is, in a meaningful sense, the planet's nervous system, a distributed array of listeners, spread across every continent and many ocean islands, constantly monitoring the Earth's interior activity. When an earthquake occurs anywhere on the globe, the waves it produces arrive at stations around the world in a sequence determined by their travel paths and the structure of the Earth's interior. Scientists can use those arrival times to locate the earthquake with remarkable precision, even if it occurred in the middle of an ocean or beneath a remote mountain range where no human observer was present. This network has taught us more about the deep Earth than any other tool we possess. The way seismic waves bend and reflect and change speed as they travel through the planet has allowed scientists to map the boundaries between the crust and mantle, between the mantle and the liquid outer core, between the liquid outer core and the solid inner core. We know the approximate temperature and composition of Earth's interior not because anyone has ever been there. The deepest borehole ever drilled reached only about 12 kilometers, barely scratching the surface of a planet whose radius is over 6,000 kilometers, but because of what seismic waves have told us on their way through. The Earth speaks in vibrations. And we have learned, slowly and carefully, how to listen. The seismic waves that travel through the Earth after an earthquake do not simply announce the earthquake's occurrence. They carry information, deep, structural information about the interior of a planet that no instrument has ever directly sampled below a trivial depth. Reading that information is one of the most powerful things modern geophysics can do, and the analogy that scientists themselves often reach for is a medical one. When a doctor orders a CT scan or an MRI, the machine sends waves through the body and measures how those waves are absorbed, deflected, and returned. Different tissues respond differently. Bone and soft tissue and fluid each interact with the waves in characteristic ways, and from the pattern of those interactions, A detailed image of the body's interior can be reconstructed without a single incision. The body is never opened. The structures are revealed entirely by what the waves say on their way through. Seismic tomography works on the same principle, applied to a planet. Earthquakes generate waves that travel through the Earth in all directions, and seismographs around the world record their arrival times with great precision. By comparing the actual arrival times to what those times should be if the Earth were a simple, uniform sphere, scientists can identify regions where the waves traveled faster or slower than expected. Faster travel usually indicates cooler, denser rock. Slower travel often indicates warmer, less dense material, perhaps a rising plume of hot rock from deep in the mantle, or the subducted remnants of an ancient oceanic plate sinking slowly into the deep interior. Over decades of accumulating data from thousands of earthquakes and thousands of recording stations, seismologists have assembled a three-dimensional portrait of Earth's interior that is genuinely remarkable in its detail. The great subducting slabs of oceanic crust, including ones that descended into the mantle millions of years ago and have been sinking slowly ever since, are visible as fast-velocity anomalies threading downward through the mantle. Hot mantle plumes, thought to be the source of volcanic hotspot chains like Hawaii, appear as slow-velocity columns rising from deep within the planet. The boundaries between the major layers of the Earth, crust, mantle, outer core, inner core, are resolved with increasing sharpness as more data accumulates. This is not science conducted from a safe remove from geological time. It draws on earthquakes that are happening today, and also on the records of earthquakes that happened long ago. Because seismic waves leave physical marks in the landscape, offsets in rock layers, displaced sediment, deformed terrain, the geological record of past earthquakes extends far beyond the era of instrumental seismology. The science of paleoseismology involves the careful excavation and analysis of trenches across fault zones, looking for the preserved signatures of ancient ruptures. A fault that broke the surface centuries or millennia ago will often leave a clear and readable record in the stratigraphy of the soil, a sudden offset between otherwise continuous sediment layers, a colluvial wedge of material that accumulated against the newly created scarp, organic material that can be dated with radiocarbon methods to give an approximate age for the event. Through this work, scientists have extended the earthquake history of many fault zones back thousands of years, revealing recurrence patterns and average recurrence intervals that could never be inferred from the short instrumental record alone. The Wasatch Front in Utah, the Hayward Fault in the San Francisco Bay Area, the Alpine Fault in New Zealand, all have paleoseismic records that speak of large earthquakes occurring repeatedly over geological time, following patterns that inform present-day hazard assessments with a depth of historical perspective that no written record could provide. This kind of deep, patient reading of the Earth's history owes something to the earliest scientific thinkers who tried to understand earthquakes at all. One figure in particular deserves mention, not because his ideas were entirely correct, but because he was among the first to approach earthquakes as natural phenomena governed by physical principles rather than divine punishment or supernatural cause. John Michell was an English geologist and natural philosopher working in the 18th century, a man whose contributions to science range from the theory of magnetic fields to the first quantitative treatment of the concept of what we would now call black holes. In 1760, following the Great Lisbon earthquake of 1755, an event that had shaken the philosophical as well as the physical foundations of European thought, Michel published a paper in which he argued that earthquakes were caused by waves of pressure moving through the earth, generated by the sudden vaporization of water coming into contact with underground fires. The mechanism he proposed was wrong, rooted in the limited geological understanding of his era. But the framework was revolutionary. He was asserting that earthquakes were physical events with physical causes, that they produced waves analogous to those in water or air, that those waves could be studied and their origins inferred from their behavior. He was, in essence, proposing the scientific study of seismology nearly a century before the word seismology existed. His intellectual instinct, that the earth was a physical system, that its convulsions obeyed natural laws, that those laws could in principle be discovered, was entirely correct and pointed directly toward the science that would eventually develop. Now, if we follow the history of earthquake science forward through the centuries and into the present, we eventually arrive at one of the most persistent questions in the entire field, a question that has been asked by scientists and lay people alike, that has generated countless research programs and an enormous literature, and that remains, despite all of that effort, substantially unanswered. Can we predict earthquakes? To approach that question honestly, it is worth clearing away some of the folklore that has accumulated around it. There is a widespread belief in parts of the world that certain weather conditions precede large earthquakes. Hot, still air. Unusual humidity. A peculiar quality to the light or the atmosphere. Earthquake weather, people call it, describing conditions they are convinced are associated with imminent seismic events. This belief is ancient, appearing in writings from ancient Greece and persisting in various forms across cultures to the present day. The scientific evidence for earthquake weather is simply non-existent. Earthquakes occur in all seasons, in all weather conditions, at all times of day and night, during storms and droughts, in heat and in cold. The rupture of a fault 10 or 20 kilometers underground has no mechanism by which it could be influenced by or coupled to surface atmospheric conditions. Studies that have examined the question statistically have found no correlation between atmospheric weather and earthquake occurrence. The belief persists because human memory is selective. We remember the hot, still day before the earthquake and forget the dozens of hot, still days on which nothing happened. Groundwater, on the other hand, is a different matter. There are credible and replicated observations of changes in well water levels and in the chemical composition of groundwater in the period before some earthquakes. The proposed mechanism involves the compression and dilation of rock as stress accumulates along a fault, subtle deformation that might affect the pore pressure and flow of groundwater in the surrounding region, producing measurable anomalies in wells before a large rupture occurs. Some researchers have documented these kinds of changes in the days or weeks before significant earthquakes, and the observations are intriguing enough to warrant serious study. The challenge is consistency. Not every earthquake is preceded by detectable groundwater anomalies, and not every groundwater anomaly is followed by an earthquake. The signal, even where it exists, is not reliable enough to serve as a predictive tool. It may eventually contribute to a broader ensemble of precursory indicators, but it cannot stand alone. The question of animal behavior before earthquakes is one of the most enduring and emotionally compelling in this field, and it is taken more seriously by some researchers than popular accounts might suggest. The observations themselves are numerous and cross-cultural. Unusual behavior in animals: dogs barking without apparent cause, cats hiding, livestock refusing to enter barns, fish behaving erratically, snakes leaving their burrows in winter, has been reported before significant earthquakes in many parts of the world over many centuries. In China, where animal behavior monitoring was at one point incorporated into official earthquake prediction programs, there are accounts of unusual animal activity preceding the 1975 Haicheng earthquake, one of the few cases in which a significant earthquake was successfully predicted and an evacuation ordered in advance. Whether animal behavior constitutes a genuine and reliable precursor is debated, but the plausible mechanisms are not entirely speculative. Animals may be sensitive to the very small precursory seismic events, microearthquakes and tremors too small for humans to feel, that sometimes precede larger ruptures. They may be sensitive to changes in the local electrical or electromagnetic environment, which some researchers believe can be altered by the piezoelectric effects of stressed rock. They may detect changes in groundwater chemistry, infrasound, or ground tilting that is too subtle for human perception. Any of these mechanisms would provide a sensory signal to an animal that its environment is changing in some unusual way, without the animal having any conscious understanding of what that signal means. The difficulty is rigorous documentation. Anomalous animal behavior is typically reported after an earthquake, in retrospect, which introduces powerful selection and recall biases. The animals that behaved strangely before the earthquake are remembered, the animals that behaved normally are not. Prospective studies, in which animal behavior is monitored continuously and independently of whether an earthquake occurs, are far more demanding to design and conduct, and the results so far have been mixed. The question remains genuinely open. There is another phenomenon associated with earthquakes that sits at the edge of the documented and the mysterious: earthquake lights. These are reported luminous phenomena, glows, flashes, columns of light, aurora-like displays, seen in the sky or at ground level before, during, or after significant earthquakes. Reports of earthquake lights exist in historical records stretching back centuries, and they have been described in connection with earthquakes on multiple continents. Photographic and video evidence exists, including footage from the 2008 Sichuan earthquake in China and from events in Mexico. The phenomenon appears to be real. The explanation, however, is not fully settled. Several mechanisms have been proposed. One of the more widely discussed involves the piezoelectric properties of certain minerals, the ability of rocks under pressure to generate electrical charge. As stress accumulates and rock is compressed and fractured along a fault zone, the theory suggests electrical charges might be generated and could propagate to the surface, ionizing the air and producing luminous effects. Plasma discharges, radon ionization, and electromagnetic induction from rapid fault movement have also been proposed as contributing mechanisms. What is known is that the phenomenon is real, that it is associated specifically with seismic activity, and that its full physical explanation has not yet been arrived at. Earthquake lights are one of those phenomena that remind scientists, and the rest of us, that even in a field as extensively studied as seismology, there remain things that are not yet fully understood. The broader landscape of earthquake prediction myths has been an area of active attention by earthquake scientists, who have found that misinformation can cause real harm, unnecessary evacuations, public panic, erosion of trust when false predictions do not materialize. A major earthquake in L'Aquila, Italy, in 2009 was preceded by a series of small tremors and a controversial prediction by an amateur scientist, using methods not accepted by the scientific community, that a major earthquake would not occur. When a deadly earthquake did strike shortly afterward, the public backlash was severe. The episode highlighted how important it is for scientists to communicate probabilistic hazard information clearly, and how much damage can result when unofficial and unsupported predictions enter public discourse. And this brings us to one of the most important distinctions in all of earthquake science, a distinction that sounds subtle but carries enormous practical weight. There is a difference between prediction and forecasting, and it matters deeply. Earthquake prediction, in the strict scientific sense, means specifying in advance the time, location, and magnitude of a future earthquake with sufficient precision to be useful for emergency action. A true prediction would be something like, a magnitude 6.8 earthquake will strike within 50 kilometers of a specific city in the next 72 hours. That is the standard most people implicitly have in mind when they ask whether earthquakes can be predicted. And by that standard, no reliable, repeatable method of earthquake prediction currently exists. Despite decades of research and many proposed precursory signals, no technique has been demonstrated to produce useful, consistent predictions across multiple earthquakes and multiple tectonic settings. Forecasting is different, and forecasting is something seismologists do quite well. A forecast does not name a specific event at a specific time. Instead, it expresses probability over defined time periods. The Uniform California Earthquake Rupture Forecast, for example, estimates the probability that any given fault segment in California will produce an earthquake above a given magnitude within a specified period, 30 years, 50 years. These forecasts are based on fault geometry, slip rates, paleoseismic history, and the current state of stress along monitored fault zones. They are updated as new data becomes available. They inform building codes, insurance rates, urban planning decisions, and emergency preparedness frameworks. Forecasting also operates on shorter timescales. After a significant earthquake, scientists can issue aftershock forecasts, probabilistic estimates of the number and sizes of aftershocks expected in the following days and weeks. These forecasts are used by emergency managers to make decisions about reoccupying damaged buildings, resuming public services, and communicating risk to affected communities. They are not perfect, but they are genuinely useful. The distinction matters because conflating prediction and forecasting leads to unrealistic expectations on one side and unnecessary dismissal of valuable science on the other. We cannot tell you exactly when and where the next large earthquake will strike. We can tell you, with meaningful accuracy, which faults are most likely to produce large earthquakes, how often they have done so in the past, what the probability of an event in a given region is over the coming decades, and what the likely shaking pattern would be if a given fault were to rupture tomorrow. That is not the same as prediction, but it is enormously useful, and it represents the honest, careful, productive frontier of what earthquake science can currently offer. The Earth keeps its own counsel about the timing of its next great rupture. But we have learned, over centuries of careful observation, how to ask it the right questions. There is a particular kind of knowledge that does not tell you what will happen, but tells you, with quiet precision, how likely it is. Earthquake science has arrived at exactly this kind of knowledge, and it is more valuable than it might first appear. The inability to predict the exact time and place of a future earthquake is a genuine limitation, and no honest scientist pretends otherwise. But the inability to name the date does not mean we are operating in the dark. What statistics and probability theory allow us to do, when applied to fault history, slip rates, stress accumulation, and the long geological record of past ruptures, is to build a meaningful picture of where risk is concentrated, how that risk varies across time, and what the relative likelihood of large earthquakes is along specific fault systems over periods of decades. This is the foundation of modern seismic hazard analysis. It draws on paleoseismology's record of ancient earthquakes, on geodetic measurements of how quickly the ground is deforming today, on the instrumental catalog of recent seismicity, and on physical models of how stress evolves along faults between major ruptures. The resulting hazard maps are not precise in the way a weather forecast is precise. They do not tell you that an earthquake will strike on a particular Tuesday. But they tell you, with genuine statistical grounding, that certain regions face significantly higher probabilities of strong shaking than others over the next 30 or 50 years, and those probabilities translate directly into decisions about where to build, how much reinforcement is needed, and how to allocate emergency preparedness resources. The Uniform California Earthquake Rupture Forecast, updated periodically as new data becomes available, provides exactly this kind of probabilistic landscape for one of the world's most studied seismic regions. Similar forecasts exist for Japan, New Zealand, Italy, Turkey, and a growing number of other countries. They are imperfect, they are models of a complex natural system, and models always involve simplifications, but they represent the most rigorous and useful translation of geological knowledge into actionable guidance that science currently can provide. What these forecasts consistently show, when examined honestly, is that the uncertainty in earthquake timing is irreducible over the short term. A fault that is thought to have an average recurrence interval of 200 years might produce its next rupture in 50 years or in 350 years. The geological clock has no second hand we can read. The variability around average recurrence estimates is large enough that pinning down a specific window of more than a few decades is not currently possible for most fault systems. The Earth's timing remains its own. This honest acknowledgement of limitation has not, however, prevented the development of something that does operate on very short timescales and provides genuine, life-saving value. Earthquake early warning systems are now operational in several countries, and they represent one of the most impressive practical achievements in applied seismology. The principle is elegant. When a fault ruptures, seismic waves travel outward in all directions, but they travel at finite speeds, several kilometers per second for the fastest P waves. Electronic signals, by contrast, travel at the speed of light. A seismic network that detects the first arriving waves at stations close to the rupture can, in principle, calculate the earthquake's location and magnitude within seconds and transmit alerts to more distant areas before the slower, more damaging S waves and surface waves arrive. The warning times involved are not long. They are measured in seconds to perhaps a minute or two, depending on how far a given location is from the epicenter. That is not much time. But it is not nothing, either. A few seconds is enough time for a surgeon to pause a delicate procedure, for a train to begin braking, for an elevator to stop at the nearest floor and open its doors, for a student to take cover under a desk, for a power plant operator to initiate a safety shutdown, for a person standing in the open to drop, cover, and hold on. These are small actions with potentially large consequences, and the accumulation of those individual actions across a city or region can meaningfully reduce the human cost of a major earthquake. Japan's earthquake early warning system, operated by the Japan Meteorological Agency, is the most mature in the world. It has been operational since 2007 and has demonstrated its value in multiple events, most notably the 2011 Tohoku earthquake, for which alerts reached much of the population seconds before the shaking arrived. Mexico has operated an early warning system for decades, focused on the subduction zone off its Pacific coast. The United States launched Shake Alert, a West Coast early warning system, in recent years, progressively expanding its coverage and public alerting capabilities. These systems are not perfect, they sometimes issue false alarms, and they sometimes underestimate the magnitude of an event in the first few seconds. But they are improving steadily as network density increases and algorithms become more sophisticated. Early warning is one layer of a much broader framework for living safely in earthquake country. And living safely, genuinely safely, is something that is achievable, even in the most seismically active places on Earth. The evidence for this is clear and encouraging. Japan, as we have noted, sits at one of the most tectonically complex and seismically active locations on the planet. And yet the Japanese people have developed, over generations and through hard-won experience, a relationship with earthquake risk that is not defined by helplessness or fatalism. It is defined by preparation, education, engineering, and community resilience. Buildings are designed and built to standards that would have seemed extraordinary even a few decades ago. Schoolchildren practice earthquake drills regularly. Public infrastructure includes clearly marked evacuation routes and designated shelter areas. Annual national drills are conducted on the anniversary of the 1923 Kanto earthquake. The cultural knowledge of how to respond to an earthquake, drop to the floor, take cover, hold on, move away from tall unstable objects, avoid rushing to exits and crowds, is deeply embedded in the population from childhood. The result is that Japan, despite the extraordinary seismicity of its geology, has reduced its per capita earthquake death rate dramatically over the decades since its worst historical disasters. The improvement is not complete, and it was not easy, and it required sustained investment and political commitment. But it is real. Seismic risk can be managed. Not eliminated, never eliminated, but managed, reduced, and lived with, in a way that preserves human life and community resilience. Which makes it all the more important to address the myths and misconceptions that, in some parts of the world, substitute for genuine earthquake safety education. Perhaps the most persistent of these is the doorway myth. For generations, people in earthquake-prone regions were told that standing in a doorway during an earthquake was the safest possible action, that the door frame would provide structural protection if the building collapsed. This advice was widely disseminated, appeared in official publications for decades, and became deeply embedded in popular culture. It is wrong. Or rather, it was true in a specific and now largely historical context, the context of unreinforced adobe construction, in which door frames were sometimes the most structurally sound part of a building. In modern construction, door frames provide no special structural advantage over the surrounding walls. And standing in a doorway leaves a person exposed to being hit by a swinging door, to falling objects from above, and to the general hazard of moving around during violent shaking. Modern earthquake safety guidance, from the United States Geological Survey, from the American Red Cross, from emergency management agencies worldwide, consistently recommends a different approach. Drop, cover, and hold on. Get low to reduce the risk of being knocked down. Take cover under a sturdy table or desk, or against an interior wall, away from windows, if no table is available. Hold on so that the furniture does not shift away from you as the ground moves. Stay in place until the shaking stops. If you are outdoors, move away from buildings, street lights, and utility wires and stay in the open. If you are in a car, pull over away from overpasses and overhead hazards and stay inside with your seatbelt fastened. These instructions are the product of research and injury analysis, systematic study of what types of injuries occur during earthquakes and under what circumstances, and what protective actions are most effective in minimizing them. They are simple. They can be taught to young children. They require no special equipment and no advanced preparation. And they work. But drop, cover, and hold on as a response to the moment of shaking. Genuine earthquake safety extends far beyond those few seconds of motion, into the preparation that happens before any earthquake occurs. Preparation encompasses many dimensions. At the individual and household level, it means securing heavy furniture to walls so it cannot topple. It means knowing where the gas shutoff valve is and how to operate it. It means keeping an emergency supply of water, food, and medication sufficient for at least several days, since earthquakes can disrupt supply chains and emergency services for extended periods. It means identifying safe spots in every room and rehearsing, even informally, what actions to take when the ground begins to move. At the community level, preparation means having practiced emergency response plans, trained volunteers, clear communication protocols, and designated meeting points where families and neighbors can regroup after an event. Communities that have invested in this kind of social preparedness, the relationships, the planning, the shared knowledge, consistently fare better in disasters than communities of equivalent size and similar physical hazard that lack those social foundations. At the governmental and engineering level, preparation means enforcing building codes that incorporate current seismic standards, retrofitting older structures that would not survive a major earthquake, mapping fault zones and restricting construction of critical facilities directly atop them, and maintaining the monitoring networks and warning systems that provide the earliest possible information when an earthquake occurs. None of this is simple. Not all of it is affordable for every community in every country. The gap between what is technically possible and what is economically accessible remains one of the central challenges in earthquake risk reduction globally. But the direction is clear. Preparation works. Education works. Engineering works. The countries and communities that have invested most seriously in these things have demonstrably lower earthquake mortality rates than those that have not, even when their geological hazard is equally severe. The Earth is seismically active. It will remain so for as long as tectonic plates continue their slow, restless movement across the planet's surface, which means for longer than any human civilization can meaningfully contemplate. The question is not whether earthquakes will occur. They will. The question is how well prepared we are to meet them, and the answer to that question is entirely within our power to shape. And with that thought, the thought of humanity learning, slowly and carefully, how to live well with the restlessness of the planet we inhabit, it feels natural to look outward. To look beyond this earthquake-prone, tectonically active, endlessly dynamic Earth, and ask a question that the space age has made newly answerable. Are we alone in having a shaking world? We are not. The Apollo missions of the late 1960s and 1970s did not only bring back moon rocks and photographs and the extraordinary image of Earth rising above the lunar horizon. They also left behind seismometers. 4 of them, placed at different locations on the lunar surface by Apollo astronauts, operated for years, transmitting data back to Earth and revealing something that surprised many scientists at the time. The moon has moonquakes. Not one kind, but several. Deep moonquakes occur at depths of around 700 to 1200 kilometers beneath the lunar surface, far deeper, relative to the moon's size, than typical earthquakes on Earth. They occur in clusters at specific locations and follow a monthly cycle, apparently driven by the tidal stresses exerted on the moon's interior by Earth's gravity. There are also shallow moonquakes, occurring closer to the surface and of uncertain origin, which can reach magnitudes equivalent to about 5 on the Richter scale, significant events. And there are thermal moonquakes, caused by the expansion and contraction of the lunar crust as it heats up in the lunar day and cools in the long lunar night, with temperature swings of hundreds of degrees Celsius occurring over the course of a month. What is striking about moonquakes, particularly the deep ones, is how different they feel from earthquakes. On Earth, seismic shaking from even a moderate earthquake typically lasts for seconds to a few minutes before the ground returns to stillness. The moon does not do this. When the Apollo seismometers detected a moonquake, the moon would ring. The shaking would continue for 30 minutes, or an hour, sometimes longer, the energy reverberating through the cold, rigid, extremely dry lunar rock with almost no attenuation. Earth's interior, full of fluid-saturated rock and a partially molten asthenosphere, absorbs and dampens seismic energy efficiently. The Moon's cold, dry, ancient interior does not. It holds the vibration and lets it ring on and on, like a bell that has been struck and then left to resonate in complete silence. This tells scientists a great deal about the Moon's internal structure, its rigidity, its dryness, its geological age and inactivity compared to Earth. The character of the moonquakes themselves is a window into a world whose geological evolution took a very different path from our own. And the Moon is not alone in this company. Mars has Marsquakes. The InSight lander, which NASA placed on the Martian surface in 2018, carried a seismometer specifically designed to detect seismic activity on the Red Planet. It succeeded. Over the following years, InSight detected hundreds of Marsquakes, ranging from small, barely detectable tremors to events equivalent in magnitude to around 5, the largest Marsquakes ever recorded. Mars is not tectonically active in the way Earth is. It does not have a network of moving plates. Its quakes are thought to arise instead from the slow, ongoing cooling and contraction of the planet's interior, the thermal stress of a world that formed hot and has been gradually cooling for billions of years, fracturing its own crust in the process. The InSight data has allowed scientists to do what no Mars mission had previously done: probe the interior of another planet directly using seismic waves. The thickness of the Martian crust, the structure of the mantle, the properties of the core, all have been inferred from the careful analysis of Marsquake recordings. It is the same technique that was used to map Earth's interior, now applied across interplanetary space. Beyond Mars, the evidence accumulates. The moons of Jupiter and Saturn are geologically active in various ways. Io, Jupiter's innermost large moon, is the most volcanically active body in the solar system, and the same tidal forces that drive its volcanism undoubtedly produce seismic activity of extraordinary intensity. Europa, with its global subsurface ocean beneath a shell of ice, likely experiences tidally driven fracturing of its ice shell, icequakes, in a sense, driven by the flexing of the ice as Europa moves through Jupiter's gravitational field. Enceladus, the small moon of Saturn that erupts geysers of water ice from its south polar region, is geologically active in ways that must involve seismic processes we have not yet directly measured. The universe, it turns out, is full of shaking worlds. Wherever there is a body large enough to have an interior structure, wherever there is mass enough to generate gravitational stress, wherever there is thermal energy cooling and contracting over geological time, there is the possibility of seismic motion. The ground shaking is not peculiar to Earth. It is a feature of planets. We live on one of the most geologically active of them, a planet whose tectonic machinery is still running at full pace, whose interior is still hot enough to drive the plates, whose oceans and continents are still being slowly rearranged by forces that have been operating since long before life appeared on the surface. The earthquakes that shake our buildings and reshape our coastlines and ring our planet like a bell are not anomalies or disasters in the geological sense of those words. They are the expected behavior of a living world, a world still in the process of becoming what it will eventually be. To lie still and think about this, the earth beneath you moving imperceptibly but persistently, the moon ringing with slow deep tremors, Mars cooling and contracting in the dark of space, Io erupting and shaking under the immense pull of Jupiter, the whole solar system populated with worlds that shudder and settle and adjust in their own quiet ways, is to feel, perhaps, something of the scale of what we are part of. Not just inhabitants of a planet. Passengers on a moving, breathing, endlessly restless geological body, traveling through a universe where the ground is almost never, truly, completely still.